Right. So if we had a reverse reaction, let's say for example, um, something which we're going to call just A becoming B. So let's often what they'll write is A plus B is equal. So often what they'll write is A plus B is reversibly reacts to form AB, and then which would mean that AB is going to in turn turn back into A plus B. But what I want to do, because it's just going to make it a little bit easier to understand, it's just A reversibly reacts to form B. I'm not saying element A or it changes to element B. I'm just saying something changes into something else. So, and these somethings could be multiple somethings as well, but something changes into something else. Okay, so so the way that we'll demonstrate this with a diagram is we'll say A are these little pink circles, and B will be these little green circles. So we start off with loads and loads of pink circles. We'll start off with a load of whatever A is, okay, and then the reaction starts, and some of these change into B, and then after a little while, maybe another one changes into B, but in the meantime, one of the B's change back into A, okay, and maybe two more of the A change into B, but in the meantime, one of them, the B's turn back into A, and so on, right? Now, this is constantly happening, and there's never a point at which the reaction finishes, because whilst A is changing into B, B is also changing back into A. However, the rate at which A changes into B will eventually match the rate at which B changes into A. So at the start, we only had A. So if I changed all that back to how it was at the start, then if I were to draw a graph now of how the rate of reaction is just for A, so maybe I'll use a pink line, it's going to start very high at the very beginning. So along the x-axis is time. I want to use a black for that. Okay, black please. So on the x-axis is time. We start off the rate of reaction for A starts very high, but as the amount of A starts to change into B, there's less of A to react, and so it's going to drop. And in fact, as that continues, it's going to continue to drop, but the rate at which it drops will reduce. We'll try to understand why that is in a moment. Eventually, it'll reach a flat line. So let's try to understand why that is. I think we need to look at what's going to happen at B in the case of B as well. At the beginning, the rate of reaction of B is 0 because there is no B to react. So we can't have it anything higher than 0 because there's nothing there. So it would start down here. However, as more and more B appears from the forward reaction, then they now have the possibility to react. But there's not much of it around, so it's only going to react a little bit. But as time goes on, more of it appears, and so it reacts a little bit more. But eventually, it gets to a point where the rate of the forward reaction is the same as the rate of the reverse reaction. So that's basically the rate of reaction. Now, it doesn't necessarily. This won't necessarily be when it's 50% of each one, because sometimes it's easier for the forward reaction to happen, or let's say one of the reactions to happen, than it is for the other one to happen. But it is definitely true that as you increase the amount of B, then the rate of that reaction increases, and as you decrease the amount of A, the rate of that reaction decreases. So this is going to be, so they always meet in the middle if it's this kind of equation, because they stop, the rate stops changing once they're both the same. So they meet in the middle and then they become flat. Now, in the meantime, we have this other graph which we can draw, and this is now the concentration of each one. So at the beginning, we had all A, right? So it was nothing but A. So again, that starts off high, and then they started to react, so it reduced. But the rate at which it reduced decreased. So the gradient became less and less and less, and so it flattened out. So far it looks the same as the above graph, but the concentration of B won't necessarily, unless it reaches equilibrium when it's 50-50, 50% of each one, then it's not going to meet at the flat line. It could do this, but it could also do this. Let's do this one. The point is, it doesn't need to, and that it should be flat. Mine doesn't look quite flat there. So make sure, I'm still not doing it flat. We don't want it to go back down again. Still, all right, whatever I seem to do, I can't stop it from going down. Make sure yours doesn't go down. It's supposed to be flat. It doesn't go back up or back down. It just gradually becomes flat. So that's time along the bottom axis again. So, yeah, so these are the two graphs that we'll see. And like I say, they don't necessarily go past each other. They could never cross each other, or they could meet each other, but it's unlikely that they're going to do the same as that. Why is it dynamic equilibrium? Because essentially the dynamic part means that it's still changing. Things are still changing. The reaction is still going on. Let's say we're at this point here. So it's equilibrium when there are three greens. Well, one green changes to A, one B changes to A, but then in doing so, one of the pink ones changed back to B, and so on. So this changes back to A, but then in doing so, in no time at all, that one's changed back to the A's changed back to B. So we never know which one's going to react, but the point is the concentration stays constant. However, the reactions are still continuing. So that's what we mean by dynamic equilibrium. So what we'll do then is try to understand how we can now shift where that equilibrium point lies. Okay.